So, how are you guys today? Okay, so for today, we're going to continue with the last topic on the motion, which is the relative velocity. Okay, so what is the relative velocity is all about? All right, so let's say you are riding a bicycle, all right, and then you see the others are on the or inside the car. So both of you are moving, all right. So each of you are seeing each other. So it's relative. Let's say you are cycling and then you see the other people inside the car. So basically, you are measuring the relative velocity of the people inside the car relative to you. All right. So and also similar to people inside the car, right, and seeing you cycling the bike. So that is relative velocity for the people inside the car towards you. Alright, so for example, we look here. So if we have a point P is moving relative to the reference frame A. Okay, so we see the point P is the passenger inside the train. Okay, so the reference frame A is the cyclist. Okay, and we denote the velocity of P. Okay, velocity of P, the passenger, relative to cyclist. Okay, as V P A. Okay, if P is moving relative to frame B, okay, and frame B is moving relative to A, then the x velocity of P relative to frame A is VPA minus x. Okay, so the first situation, so you look the P is the passenger, all right. So it's moving to relative to frame B. Okay. So for example, over there, the frame B is the train. Okay. And the frame B is moving relative to frame A. Okay. So the frame A now, A is the cyclist. And then the x velocity of the P relative to frame A. Okay, so we are looking at the velocity in terms of x direction, okay, of P. P is the passenger relative to A is VPA x, okay, which is equals to VPB, okay. So relative velocity of the passenger to the train, okay, plus VBA, okay, the relative velocity of the train to the cyclist. Okay, so basically it is all right. So VPA is actually the combination of VPB and VBA. All right, so you look there. So P relative to B and B relative to A, then it will be equivalent to P to A. Okay. Give me a second. All right, so we look at the graph. So we have okay, so the original point at OA, and then that's the cyclist time frame. Okay, and then we have OB. Okay, OB is the original point of the train. Okay, and then we have VBA. Okay, so this train is moving to the X direction, and then we have the velocity of train relative to the cyclist, so which is to the this one. All right, so it's from here. Okay, so it is related to this one. So basically VBA of course will be equivalent to XBA over T. So you obtain the relative velocity of train relative to the cyclist. Okay. All right. So we see the position of the passenger. All right. So we have a passenger now. So let's say the position of the passenger is here. Okay. So at this original point, so none of the object, okay, the cyclist and also the train is moving. But now let's see, it is moving to that direction. So we have a position X, all right, position X. So SA is the position of the uh, cyclist, all right, it's the position of the cyclist. The and also the XP is the position of the train. And we see that the passenger P now is in the moving direction. So we have the passenger is seen from the moving direction of the cyclist and also on the moving train. Okay, so we have here the position all the way. Okay, so from the cyclist to P. Okay, so this is the relative position of the passenger to the cyclist is this one, and then this is the position of the passenger to the train, the relative position of the passenger to the train. So as you can see here, VPA is the sum of XBA and XPB. Okay, so that's why we have the VPA is equivalent to VPB and also VBA. Alright, so which object that is slower will start at the left of the time frame. Okay, and then because it is moving to that direction, so you see the passenger, the point of the passenger should be here, and also the starting point of the train will be on the right side of the graph. Okay, all right, so we look at the extension of the problem. Okay, let's say we look at the velocity in 2 or 3 dimension by using the vector addition. Okay, so let's say the train is moving towards that direction. Okay, so the direction is towards outside of the screen. Okay, and then the passenger is moving to the right. Okay, so both of the train and also the passenger is having the velocity now. Okay, and then okay, we look over here. So the velocity of train relative to the cyclist. So we still have VBA, but the difference here that the position of the passenger. Okay, so we have that the RPA, okay, which is the direction, okay, the direction of the passenger to the cyclist. Okay, as you look here, okay, so that's the vector. Okay, the vector of the cyclist to the passenger. Okay, so as you can see that the passenger is moving towards that direction. Okay, mean that it goes towards that direction. Okay, so you need to have the component of the vector. Alright, so the cyclist will see this passenger at initial point starting from there, and then next it will move to that direction. Okay, so we need to quantify those vector. Okay, so basically uh, it's like that. Alright, so from there, okay, and then from there, so we have two vectors. Alright, so we look at this graph. So we have RPA, which is the vector of P, the passenger, to the cyclist, is the combination of the vector of B. So B is the train to the cyclist, with the addition of the vector of the passenger to the train. Okay, so the frame, okay, the frame of the or the axis of the train will be upward. Okay, it will be upward from the cyclist. Okay, it is because P, okay, because the train and passenger is moving in the 2D motion right now. Okay, before this, you just see that it is only to that x direction. Okay, now we see that we have the component of y and also x. Okay, so we have component of y and also x. So this is y and that is x. Okay, so all right, so that is for the 2D, the 2 dimension of the relative velocity. Okay, we look at the example here.
In example 3.15, we'd like to explore how the pilot in example 3.14 can correct for the 100 km/h crosswind. So here's a vector diagram of the various velocities in the problem. This is essentially a two-dimensional relative velocity problem. The velocity of the plane with respect to the air always has a magnitude of 240 km/h. However, we want it to fly a little bit westward to cancel out some of this 100 km/h eastbound wind. In fact, we need to cancel it in such a manner that the plane's trajectory is due north. We will appeal to equation 3.35 that says the velocity of the plane with respect to the Earth is equal to the velocity of the plane with respect to the Earth, to air plus the velocity of air with respect to the Earth. And we know something about all three of these velocities. Velocity of the plane, the speed of the plane with respect to the Earth is unknown. However, we know that it must be due north. That's what we are requiring. Velocity of the plane with respect to the air always has a magnitude of 240. That's its speed, but we don't know its direction. And finally, the velocity of the air with respect to the Earth, both its magnitude and direction are known as 100 kilometers, and it's due east. We can execute a solution to this problem by recognizing that this forms a right triangle, and we're actually going to first calculate the magnitude of this side of the triangle, and that of course is obtained by squaring the hypotenuse and subtracting this side, which is 100 kilometers per hour squared, and taking the square root, and it's 280 kilometers per hour. The angle is obtained by noticing that the sine of beta is opposite over hypotenuse, so beta is equal to the arc sine of this ratio, which is going to be 25 degrees west of north. When we look at the solution, we note that the actual velocity or speed of the plane relative to the Earth is somewhat less than the airspeed. And this, of course, is a consequence of the crosswind. In fact, we're angling this vector p slash a in such a manner that its x component, or its eastbound component, is exactly cancels the eastbound component of the crosswind. This ends example 3.15.
Okay, so we look here. So this is actually the more, I mean, the in the real world problem. So this is what actually we are looking for the relative velocity. So when we are traveling on the plane, so the pilot needs to use the relative velocity because the Earth is moving as well. All right. So at the same time, so the plane is moving and the Earth is moving. So we need to calculate the relative velocity in order for the pilot can know the the direction of the plane is actually to moving towards the correct direction. Okay, so let's say we have here right now in the problem, so we have the wind and airspeed, so as given in the example. Okay, in what direction should the pilot had to travel, okay, to the north? All right, so what will be the velocity, okay, relative to the Earth? All right, let's say we have, okay, so magnitude unknown. All right, so we need to determine first what is VPE. All right, so plane to Earth. So let's say we have the combination of VPA, okay, VPA, and then plus VAE. Okay, so we look here. So we have the VAE, okay, VAE. Okay, we have the wind speed, all right, with the wind speed and also the airspeed. Okay, so the wind speed is 100 km per hour, all right, towards east. Okay, and then we have the we have the airspeed. Okay, the airspeed we know, but the direction we don't know. All right, and then we know the final direction. Okay, the final direction is towards north, but the magnitude of the final direction we don't know. Okay, so we construct that in terms of a triangle. Okay, so we know that the direction of the relative velocity, okay, the relative velocity, which is the final one. So the combination of the wind and air speed. Okay, the wind and air velocity. Okay, so we have the V. Okay, we mentioned that the final one. So VPE. Okay, so the VPA is the air speed. Okay, so plane to air. Okay, and then VAE, air to the wind. Okay, air to the wind, right? So we have that one as 100 kilometer per hour, or the wind we can consider that as the earth. All right, so we have the plane, plane to the air, okay, and air to the earth. All right, so we construct that. So assume that that direction, okay, that direction is combined with the with the initial point of the VAE. Okay, because we know that direction of the VAE is due to east, so we combine the component of the vector. All right, so but right now we still don't know what is the right direction, so it can be either to the left side, okay, or to the right side. We don't know. Okay, but the important thing is we want to make sure that the plane is moving towards the north. Okay, so how do we solve that? But what we know is the speed, all right, is the speed of the plane, all right, the speed of the plane, and also the speed of the wind. Okay.
Example 3.1. So here's a little bit that the plane's trajectory is due north.
Okay, so
we will appeal to equation 3.35.
we look
It says
here.
the velocity of the plane with respect to the Earth.
All right, now
is equal
we
to the
can,
velocity of the plane
when we
with respect to
construct the graph,
air,
so we know
the
that
velocity of air with respect to
the
Earth.
hypotenuse will be 240,
And we know something about
and
all
then
three of these velocities.
the side
Velocity
on the
of
top
plane,
will be
the speed of the plane with respect to
100.
the Earth is unknown.
Okay,
However, we know that
so
it must be due
basically
north. That's
we can know what is the velocity towards the
velocity of the plane
north.
with respect to the air always has the magnitude
Okay,
of 240.
as
That's
long
the
as
speed
we know
moving in
what
this
is the
direction.
angle.
And finally, the velocity
Okay, what is the angle
air with
made
respect to the Earth, both its
between
magnitude and direction,
the
are known as
plane
100
velocity
kilometers
towards the
degrees.
north and the,
We can execute a solution to this
all right,
problem by recognizing that this
and
function is a
the
triangle.
direction of the
We're actually
plane.
going to first
Okay,
calculate the magnitude of
sorry,
the center of
the
the
speed of the
triangle.
plane
And that, of course,
at
is obtained by
240.
squaring the hypotenuse and
All right,
subtracting this
so
side,
basically,
which is 100.
okay, so basically we know that the VPE, okay, so assume that this is X and this is Y, right? VAE is Y, and then the VPE is X, and the VPE is Y, and VAE is X. So X squared plus Y squared and square root of that. Okay, so you square the VAE and add that with the square of VPE, and then square root of that, so you will obtain 240. All right, so reverse to that problem, so the VPE will be equals to square root of VPA squared minus VAE squared. Okay, so that's how you obtain 218 for VPE. Okay, but you need to know what is the angle. So now you know the magnitude. Now we can know the angle. beta, that is that the plane should travel, okay, in order for the pilot heading towards north. Meaning that it needs to maintain the speed at 240 km per hour, but the pilot need to steer to what degree of angle to ensure that the plane is moving towards north. Okay, so that's why we need to have the beta, which is the angle. So the arc sign, so will be, so we take the sides, all right, of the VAE, which is 100, and then divide that with the hypotenuse, right, which is 240 km per hour. So we get that as 25. Okay. So we take the opposite side, divide with the hypotenuse, so we obtain the angle.
The sine control velocity, and this of course
Okay.
is pulling.
All right, so that's it for the relative velocity for the 2D motion. For the 3D, it will be more complicated, okay? So because that one will involve the z direction. But let's say, okay, we go back to the cyclist problem. Okay, if we are considering for 3 dimension, let's say, okay, you see that the train is moving, let's say, at the second level, and then the cyclist at the ground level inside the building, right? So for example, like that, then we will have the 3 dimension of the relative velocity, because the cyclist is not on the same level of the train anymore. Okay, now we have the 3D. So to solve that 3D problem, of course, your vector will be also in the 3 components. So it will be in X, Y, and so it will be more complicated. But for now, we are considering only 2D. Okay. All right. So any questions so far? So that's it for the chapter of motion. After this, we're going to continue with the Newton's law. All right. Okay, so let's continue with the chapter 4. So now we have the Newton's law of motion. Okay, so for the Newton's law, so basically it will describe the motion. All right. So what you will learn here, so it's about the concept of force. So force is the one that, let's say we have the object and then we push the object, so we have the force. Okay. So why the force are vectors and the significance of the net force of an object. Okay. So what happens, okay, when the net force of an object is 0, okay, and then the acceleration, the object, okay, and then now we are considering about the mass and object and the weight of that, and then the force. Okay, so the first 3 chapters, we seen that we learn about the kinematics. All right, so we describe the motion in 1, 2, or 3 dimension. Okay, but over there we are considering the object is already moving. Okay, we consider the object is already moving. So what caused the object to move? All right, so to ensure that the object move, we need to have a force that move that object. Okay, so to learn that, we need to learn about the dynamics. All right, so whenever we have the force that move the object, we learn about the dynamics. Okay, so the principle of the dynamics, okay, is clearly stated for the first time by the Sir Isaac Newton. That's why we have the Newton's law of motion. Okay, the Newton, okay, Sir Isaac Newton did not derive this law, but he rather deduced them from a multitude of experiments performed by the other scientists. Okay, so basically, the Newton is the theorist, all right, where he can derive the mathematical equation, all right, to support the experiment done by the previous scientists. Okay. Okay, so we look at the properties of the force. Okay, a force is a push or a pull. So it can be you pushing an object or you pull that. Okay, so you pull that. Okay, a force is an interaction between two objects or between an object and its environment. A force is a vector quantity with magnitude and direction. So of course it is a vector quantity because you can move in any direction. Okay, because we need to consider that direction and also the magnitude of the force. So we have 4 common types of force. First one is the normal. Okay, so normal force is when an object rests or pushes on a surface. Okay, and then the surface exerts a push on it that is directed perpendicular to the surface. For example, we have the normal one, the surface is horizontal. So the normal force will be perpendicular to that. Okay, it will be normal. Okay, and then you look at the right picture. So let's say the surface is making an angle. Okay, so we have, let's say the angle is at 45 degrees. Okay, and then the force, the normal force will be perpendicular to that. Okay, so it will be, okay, so it will be 90 degrees from the surface of the ground. Okay, surface of the ground. Okay, so the normal force is a contact force. So the normal force is called as a contact force. Okay, now we have the friction force. So the friction, okay, because we need to consider the roughness of the surface. Okay, so because the friction is considered when the object is moving towards any direction. Okay, so the is called that the based on the surface. All right, so that is directly parallel to the surface. So it is in the same direction of the surface. The friction is also a contact force. Okay, so so we already have two types of force. First is normal, and then the second one is the friction. And then we also have a tension force. So tension is the pulling force exerted on an object by a rope. Okay, so you have a tension. Okay, so mean that we have then external object that pull the object. The tension is also a contact force. Okay, so we already have normal force, friction force, and also tension force. Okay, and the last one, we have the weight force that is acting, okay, towards the pull of gravity. Okay, and it's a long range force. Okay, a force that acts over a distance. Okay, so except this, the weight is a long range force. So it is not a contact force. So for those three, for the previous three, that are the contact force, but the weight is the long range force. Okay, what are the magnitudes of the common forces? Okay, so let's say we have the SI unit of the magnitude of the force in the Newton. Okay, some typical force of magnitudes. Let's say we have the sun gravitational force. Okay, and the weight of a large blue whale. Okay, the maximum force of the locomotive. Okay, so that's those example. Okay, so the weight. So the weight is a force. Remember that weight is a force, but the mass is not a force. Okay, so a pulling force. Okay, and then, all right, what else are different? So the attraction. Okay, electric attraction is also a pulling force. All right, it's a pulling force. All right. So okay. Now we want to draw the force vectors. Okay. Okay, for example, we have the figure there. So the figure shows a spring balance being used to measure a pull that we apply to a box. Okay. So we draw a vector to represent the applied force. Okay, so what force that is acting over here? Okay, so we have the normal force. Okay, what we learn. So we have the friction force. Okay, we have the tension force, and also we have the weight force. Okay, the line of the vector shows the magnitude. Okay, the longer the vector, the greater the force magnitude. Okay. Alright, let's say we have the superposition of the force. Okay, so let's say we have multiple forces, and then we combine that together. So that will be a superposition of forces. Okay, let's say we have F1 and F2 as the two forces acting on an object at point O, and then have the as a single force. Okay, because combination of F1 and F2 will be equivalent to vector R. Okay, several forces acting at a point on an object have the same effect as their vectors subacting at the same point. Okay, as long as they are acting at the same point, so you can combine those forces. All right, so we can also decompose. So we know that we can combine, and then we can also decompose. All right, so let's say we have a force F. All right, so for example that, so we can decompose that into the X and Y component. All right. So, okay, we look at the example.
Example 4.1, 3 wrestlers are fighting over a champion's belt. Each wrestler applies a force to the belt as shown in this diagram. The largest force, F1, makes an angle of 53 degrees respect to the minus x-axis. F2 is along the positive x-axis, and F3 is along the minus y-axis. The three forces are actually given in polar notation where we have their magnitudes and their directions. And what we'd like to do is put these forces in component notation, then add them together to get the resultant force as shown on the right. Of course, the two components of resultant force are obtained by summing the respective components of the three forces in the diagram on the left. So Rx is the sum of all the Fx's, and Ry is equal to the sum of all the Fy's. Now, to get these components, we'll need the angles. In particular, we'd like to have the angles with respect to the positive x-axis. Again, theta 1 is respect to the minus x-axis. So we take 180 degrees and subtract that 53 degrees from it. We have the angle with respect to the positive x-axis, as shown here. Theta 2, of course, is 0 since that vector is along the positive x-axis, and theta 3 is 270 since it's straight down. Well, only the first force will have two components, or two non-zero components, and those are given, of course, by the magnitude times the cosine of 127 degrees for the x component, and the magnitude times the sine of 127 degrees for the y component. F2x is the full magnitude of the vector along the x direction, of course, and it has, F2 has no y component. That's going to be 0. So here's F2y is equal to 0. F3 has no x component and only a y component, which is minus 120. So it's a simple matter now to get the components of the resultant vector. And from these two components, I can calculate the magnitude of that vector, which is going to turn out to be 128 newtons. You can also find the angle that that vector makes with the positive x-axis by taking the arctan of the ratio of the y component to its x component, and that gives me an arctan of minus 0.8, which will give me an angle of minus 39 degrees, and that would be down in this quadrant here, but I know that's not correct because F1 is the largest force. That's the one that's going to dominate the resultant. So I've got to add, as usual, the arctan will not give me the answer. It only gives me the answer up to 180 degrees. So I've got to add 180 degrees to it, and I get 141 degrees. We can evaluate this solution by just looking at the sum of these vectors graphically. I can do that very briefly by taking F2 and displacing it and starting it at the head of F1. It will come out like this. And then I can add F3 to that one. That brings me straight back to that. And so I can see that graphically, indeed, my resultant vector lies in the second quadrant as expected. This ends example 4.1.
Okay. Alright, so what's the problem is asking, so we have the three professional wrestlers are fighting over a champion belt. And okay, so we have figure 4.7a shows the horizontal force each wrestler applies to the belt. Okay, so we have three forces. So we have F1, F2, and F3. Okay, so the F2 and F3, we don't have a problem with that because it is only on one single direction. Okay, so F2 will be on the x direction and there will be no y component, right? And then F3 is in terms of y direction, so we have no x component. Okay, so we already given the magnitude of the forces. F1 is 250, F2 is 50, and F3 is 120. Okay, so we are requested to find the X and Y components of the net belt and finds its magnitude and direction. Okay, so first what we need to do is, because F1 is in both X and Y direction, so we need to decompose to X and Y direction. Okay, so let's say we have an angle there. All right, angle of F1, so that is 127 from the x-axis. Okay, and then we have F1. Okay, so F1x will be, so in terms of x, it will be 250 times cos 127. Okay, so we obtain minus 150 Newton. And then F1y, okay, to the y direction. So we have 250 times sine 127. Okay, so we obtain 200. Okay, and we have F2. So F2 in terms of x direction. Okay, so we have cos 0 because the angle is 0. Okay,
Axis. This decompose.
all right. And we have another one for F3. Okay, so we have F3 as 120 Newton times cos 270. Okay, and then we also have as F2y. All right, F2y, of course it will be 0. Okay, of course it will be 0 because there is no y direction. Okay, so we can know what is the magnitude right now. So by adding of the same vectors, right? By adding the magnitude of the same vectors. So let's say to the x direction, so we have f1x plus f2x and plus f3x. Okay. And then similarly for the y component. So for Rx, so which is the force towards the x direction, so we have 128 Newton, right? And then what is the angle? Okay, what is the final angle made, right? Because we don't know, because initially we can obtain what is our x and y. Okay, so since x to the left direction and y to the opposite direction, we or to the north direction, so we have the resulting force will be on the quadrant number 2, which is on the quadrant of F1. Okay, so theta we obtain as 141. All right, so that's it. Okay, that's it on how to solve on the superposition of the forces. All right. Okay, so let's take a 5-minute break. Okay, before we continue. Okay, so I'm going to stop for 5 minutes and then we'll continue. Any questions so far? Okay.
I could turn back time. Hi.
Okay. Let's continue. All right. So now we already know how to decompose all of the three vectors. Sorry, the vectors of the force, and then we also know how to combine the forces, the vectors of the forces. Okay, and then as we can see that the final force, or when we combine all of those, all right, so we call that as the resultant of the forces, or the net force. Okay, so the final force that we obtain, we call that as the net force. So the net force is equivalent to the summation of the forces. All right, the sigma sign over here is the summation of all the forces. Okay, so let's say now we are into our first Newton's law. All right, so what is the first law of Newton? So when an object is either at rest or moving with constant velocity, okay, if it is at rest, okay, so it's not moving, and then if it move at a constant velocity, meaning that the acceleration is zero, okay, so it is in a straight line with constant speed, and we say that object is in equilibrium. Okay, so remember that in equilibrium mean either is object at rest or moving with constant velocity. It's not just at rest. Okay, it can be the condition of the object moving but with constant velocity. For an object to be in equilibrium, it must be acted on by no net force. Okay, sorry, by no forces. Okay, or by several forces such that their vector sum, that is the net force, is zero. Okay, so either it act by no force, okay, or by several forces, but the combination of the forces cause the net force will be zero. Okay, so that's the first law of Newton. Okay, the net force, okay, causes acceleration. Okay, let's say for example we have a hockey puck accelerates in the direction of a net applied force. Okay, a puck on a frictionless surface accelerates when acted on by a single horizontal force. So we have the force from a different object. Okay, so let's say a hockey puck on that direction, on one direction. So giving a force of F1 towards the ball, right? The hockey ball, and then the hockey ball, of course, because from the rest, okay, from the equilibrium condition, will move according to the force acting on it. So now it will move on the x direction, which with an acceleration. Okay. Okay, when the net force is 0 and then the acceleration is 0. Let's say we have example, we have another player, okay, putting the hockey puck to that ball as well. So we have both forces exerted on the ball. And then if the force, if the force, that the, okay, let's say you swing the hockey puck, let's say you are player 1 and then your friend as player 2 also swing the hockey puck. But both of you are swinging that using the similar force. Of course, the net force acting on the ball will be 0. Okay, so when the net force is 0, of course the ball will not move, right? So this is in the theory. Okay, so let's say when you are playing hockey, okay, so you can see that, so when the other person, when the other player having force higher than the other player, even though both of them are hitting the ball, okay, so the ball will finally move to the direction where the, according to the direction where the force is higher. Okay, so let's say the player 1 give the force higher, okay, let's say towards the acceleration, and then the player 2 giving the force lesser but towards the negative acceleration. Of course the ball will move to the right. Okay, the ball will move to the right. Okay, so that's the concept of the Newton first law. Right, so we mentioned that a net force is happening when the acceleration is 0 or that the velocity is constant, okay, or the object is at rest. Okay, we have another example of, let's say, this child is sledding on snow. All right, so let's say we have, okay, the downward force of gravity acting on the child and the sled, okay, is balanced with an upward normal force exerted by the ground. Okay, so now the child is not moving, okay, because the sled is balanced, okay, by upward normal force and also exerted by the ground, which is the gravitational force. Okay, so you remember that we have 4 types of forces. So we have weight, okay, we have weight, okay, we have the tension, so we have the pulling force, okay, and then we have the normal force. All right, so now we have normal force and also the weight force, okay, and then the adult foot exerts a force, a forward force that balances the backward force of friction on the sled. Okay, so before this we have a friction acting on the sled. Okay, but now when the adult, okay, kick, okay, kick the sled, okay, so of course the sled will move. Okay, okay, when the sled is moved, it says here that there is no net external force on the child and sled. Okay, and so they slide with the constant velocity. Okay, because usually on the snow ground, so the friction will be very less. Okay, friction will be very small or very less, because, okay, when the sled is moving to, let's say, x direction, so the friction on the negative x direction will be very less. So that's why the sled can move with a almost a constant velocity. Okay, so when the Newton's first law valid? All right, suppose you are in a bus that is traveling on a straight road and is speeding up. Okay. All right, so that's one situation where the first Newton's first law is valid. So meaning that you are moving, okay, you are moving at the same speed as the bus. Right? So meaning that you can also consider that you are at the equilibrium net force. Okay, even though you are moving, but the bus is also moving, right? The bus actually moves you, okay, using the same force. Okay, so you can also consider other motion. Let's say you are throwing a ball to your friend inside the bus. So you consider that Newton's first law. So the net force acting on you and the bus will be zero. So you can consider the motion, okay, the motion of the ball, okay, without considering any other forces. Okay, so we can consider the motion that like we studied in the first three chapters. Okay, and then let's say we have, all right, so okay, so here, okay, here we give a different example. Let's say if you could stand in the aisle of a roller skate, okay, you would start be moving backward relative to the bus, okay, as the bus gains speed, okay. So you can see that, okay, when we stand in the aisle of the roller skate, so we see that when the bus is moving to, let's say, the x direction, of course, will be there will be a jerk moment, as you can experience, like when you're standing inside the bus, right? Okay, when the bus is speeding up, so will be jerk, but your jerking will be on the different, it will be on the, let's say the bus is on the right x direction, you will be jerking on the minus x direction. Okay, so it looks as though Newton's first law is not obeyed. So there is a no net force acting on you, yet your velocity changes. Okay, so but after that, you see that you are now, okay, you are now, once you feel the jerking experience, but now you are back to the normal condition. Why that happens? Okay, because now the bus is already moving at the constant velocity. All right, so when there is no acceleration, so the bus is moving at the constant velocity, then that's why you and the bus already having the net force. Okay, so that's why over there the Newton's first law is already applied. Okay, all right, so the bus is accelerating with respect to the earth and is not a suitable frame of reference for Newton's first law. Okay, a frame of reference in which Newton's first law is valid is called the initial frame of reference. Okay, so the moment that when we have the net force, okay, when the bus is not accelerating, so we call that the initial frame of reference. Okay, so remember the term. Okay, let's say we have a crash test dummies. So from the frame of reference of the car, it seems as though a force is pushing the crash test dummies forward as the car comes to a sudden stop. Right? But there is really no such force. Okay? As the car stops, okay, the dummies keep moving forward as a consequence of the Newton's first law. Okay, so this is another concept of Newton's first law. So we have the crash test. Okay, for the crash test, of course, let's say, okay, you are inside the car, all right? So let's say this picture showing you the person inside the car. Okay, so this is inside the car. All right, so it's inside the car. All right, so this is the airbag. Okay, as you can see that. All right, so when the crash is happening, all right, so you can see, as I said, select the bus, so there will be a jerk moment. All right, so when the car comes to a sudden stop, the car stop when it hits an object. Okay, then of course you will be moving forward, because at that time, okay, at that time you are no longer on a net force. Okay, because the car already deaccelerate, so meaning that the acceleration is going down, but you yourself is still at the acceleration of the car. So that's why there will be a jerk moment, so your body will be pushed towards, okay, towards the front of the car, or towards the dashboard. Okay, so that's why we need to protect you with the airbag, okay, to ensure that no further consequences happen, right? So that's also the concept of the Newton's first law. Okay, all right, so an object undergoing uniform circular, so now we are considering the circular motion. Okay, so we already learned that in the chapter 3. Okay, so as we already seen, an object in uniform circular motion is accelerated toward the center of the circle. Okay, of course, with the constant velocity, as we know that the acceleration will be moving towards the center of the circle. So the net internal force on the object, okay, must be point toward the center of the circle. Okay, so the net force will be pointing towards the center of the circle. Okay, so we look for another example. The acceleration of A of an object is directly proportional to the net external force, okay, on the object. So let's say we have example over here. So the total summation of the force will be equal to F1 over here. So we have the mass, okay, over here, and then there is an acceleration because of the tensional force, okay, because of the tension force. So when we have that the constant net external force equals to F1, so F1 is towards the x direction, okay, so we have a constant acceleration. Okay, so actually we are seeing when there is a force, then there will be only the velocity and acceleration. Okay, all right, so it is proportional. Okay, the acceleration is proportional to the external force, okay, applied on the object. Okay, so let's say if we if we pull two times stronger, of course the acceleration will be double, so it will be equivalent, okay, to the force that you applied on the object. Okay, but now you make it slower. All right, you make it slower. So now let's say you solve it by the half, so it will be back to the normal A. So normal, the first one, the first acceleration, and then you make it half more slower. All right, so now it will be half of your original force. Okay, so that's the concept of acceleration and the force. Okay, right, now we look at the mass. Okay, the acceleration of an object is inversely proportional to of the object mass if the net external force remains fixed. Okay. A non-net external force cause an object with mass m1 to have an acceleration a1. Okay. Applying the same net external force to a second object and noting the acceleration allow us to measure the mass. Okay, so we can measure the mass by having the similar forces acting on the different object. Okay, let's say we are staking both objects together, so both of them are having different mass. All right. Okay, so how we want to know the acceleration? Okay, that's how we use the second law of Newton. All right, second law of Newton, which is the Newton's second law of motion. All right, so this is the famously equation of F equals to ma. All right, so what we have, okay, so the answer is like, so you are moving, let's say you have the phone and you are forcing that phone, okay, to the x direction, okay, with a certain force, and then let's say you have another object stacking on the phone, right? You are pulling that on also on the x direction. Okay. Of course, when the mass is higher, but you are acting using the similar force, what will happen? Of course, the A will be slower. Okay. The concept is that, okay, so we have this object, let's say this is the calculator. So we pull off the certain force. All right, we put that with a certain force. Okay, so it will produce a certain acceleration, and then the object, let's say the phone, so we put that on the x direction, so we have another force, right, pulling that. So the summation of the two forces that you apply to this object and this object will be equivalent to the, okay, m1 multiply m1 times a1 plus m2 times a2. Okay, and finally you obtain the net forces. All right, so that's how you quantify it. So the sum of forces, so we have the mass of object and times dA, right, times dA. Okay, we look at example over here.
Example 4.4, a worker applies a constant horizontal force of magnitude 20 newtons to a box of mass 40 kilograms that's resting on a frictionless surface. We'd like to calculate the acceleration of the box. Let's begin with a diagram of the system. Here's the worker, here's the box. We'll take this as the positive x direction, and this is the positive y direction. You can see there are three forces. There's the applied force of 20 newtons, there's the weight of the box down, and there's the normal force pushing up on the box due to its contact with the surface. In fact, there'll be no motion in the y direction, so these two forces won't play any role. To calculate the acceleration, we'll use Newton's second law, as stated here, where we've divided the forces into their components, and we get the respective accelerations in each direction in the problem. Since the box is only moving in the x direction, we'll only consider the Newton's second law in that direction, which says this should be a subscript x in this equation. The sum of the forces in the x direction, which is only 20 newtons, there's only one force, is equal to the mass times the acceleration. We calculate the acceleration, and we get a half a meter per second squared. However, we could go back and look in the y directions and apply Newton's second law there also. So I have the normal force up, the weight is down, hence the minus sign, is equal to the mass times the acceleration in the y direction. But by inspection, I know that AY is 0, so this is going to be equal to 0, which means that the normal force is simply equal to the weight. And this ends example 4.4.
Okay, so we have a problem here.
Example 4.4.
So let's say,
applies.
okay, a worker applies a constant horizontal force with 20 Newton, okay, to a box, okay. So a worker applies constant force with a magnitude of 20 Newton, and then with mass of 40 kilogram resting on a level floor with negligible friction. Okay, so we don't consider friction here.
Y direction. Let's see, there are 3 forces.
All right.
There's the applied force.
So we have now 3 forces.
The weight of the box down.
Okay, because we don't
normal
consider
force
friction.
pushing up on the box due to.
Okay, so we have the normal force, right? Of course, and then we have the weight force, okay, which is the gravitational force, okay, and then we have the applied force, okay, with the applied force of Newton, with the pushing force, okay, 20 Newton and the mass of 40 kilogram. So what is the acceleration of the box? Of course, here, when we have, okay, the problem, okay, with the acceleration, of course, we will use the Newton's second law. All right, so as you know, the Newton's second law is the F equals to ma. All right. Okay, so we are considering, so F equals can be in either 1D or 2D or 3 direction. Okay, so for example, in this case, so we can consider that only in the 2D direction. Okay, so we consider that as net force in the fx direction and also the net force in the fy direction. Okay, so now fx, so the net force for the fx will be 20 Newton. All right, because the box will be moved with the horizontal force, so the horizontal force will be fx. All right, that will be 20 Newton, okay, and ax, so the acceleration on the x direction. Okay, now we know that, so we are already given the mass. The mass is 40 kilogram, so we can solve what is our acceleration on the x direction. Okay, that will be 0.5 meter per second squared. All right. Okay, and then the mass, okay, so do we have any component on the y direction? Okay, n, all right, so the n, the normal force minus w will be equivalent to the mass. Okay, so we don't have any acceleration on the y direction. Okay, of course it will be 0. Okay, of course, because the object is not moved, okay, towards y direction. Okay, so mean that n equals to w. All right, so because n minus w will be 0. Okay, because ay there will be no vertical acceleration, okay, because the box is not moved towards that. But if there is a slope, okay, if you are considering the slope, of course there will be acceleration vertical axis, all right, or the y-axis. All right, so that's the solution of our, so it will be 0.5 meter. Okay. All right. So we'll look at the unit. So since we use the SI system, so in the old British system, we use the force measured in pounds, distance in feet, and mass in slugs. All right. So in the CGS system, mass is in grams, distance is in centimeters, and force in dynes. All right. So in SI, so we use the kilogram for the force. All right. So sorry, for the mass we use the kilogram, and the force we use Newton. All right. And then acceleration meter per square second per second square. Right. So this is the comparison between SI, CGS, and the British units. All right, so we have the concept of mass and weight. Okay, so the weight of an object is the gravitational force that Earth exerts on it. All right, so the weight W of an object mass is given as W equals to mg. So G is the gravitational force. The value of G depends on the altitude. Okay, meaning that whenever your object will be at higher position, let's say on the top of the building, okay, compared to the ground, so the G will be different. Okay. But all right, so on other planets, G will have entirely different value, okay, than on the Earth. Okay, so we look for another example over here.
In this demonstration, I have 3 wood blocks. They are all identical wood blocks. They all weigh the same. If we take a look at the weight of the blue block, you can see it weighs about 18 newtons. Now with this setup, I have a spring scale between the red and yellow blocks. The question is, what does the spring scale read? Does it read 0 newtons, 18 newtons, or 36 newtons?
So what's your answer to this? So what the scale weight will be? Okay, any one of you want to answer that? So who chose 36 Newton? Okay, let's go back to the what he explains again.
In this demonstration, I have 3 wood blocks. They are all identical wood blocks. They all weigh the same. If you take a look at the weight of the blue block, you can see it weighs about 18 newtons. Now with this setup, I have a spring scale between the red and yellow blocks. The question is, what does the spring scale read? Does it read 0 newtons, 18 newtons, or 36 newtons?
Okay. So he asks, what is the scale reading? Is it 0, 36, or 18? So who chose 0? You can raise your hand. Okay, I mean say 0. All right. So how about the others? Okay, B. So we have 18 newtons. Who chose 18 newtons? Any of you? Nobody? How about 36 newtons? All right. So seems like only All right. So let's have a look. All right. So what reading should be?
So the scale reads about 18 newtons. Now, why does it read
Okay.
this and not 0 or 36 newtons?
All right, so the answer is 80
Well,
newtons.
The system is not accelerating, therefore the tension in the string between the yellow block and the spring scale must be equal to the weight of the block, which is 18 newtons. Another way to look at this is if you were to remove the red block and either hold the scale with your hand or attach this rope to a wall, the scale would still read 18 newtons.
Okay. So as long as the object is balanced, all right, so the spring weight will still be 80 newtons because you need to balance that. Okay, if let's say one of the object is not balanced, so it will be the difference of weight between of the two objects. Okay, all right, so right now it will be 18 newtons. Okay, so remember that. All right, so we'll continue with until finish of this chapter. So we're going to finish it within the next 3 slides. Okay. So, okay, so we have here the relationship of mass to weight. Okay, we have W equals to mg. Okay, so let's say we have the weight. Okay, W equals to mg. The summation of F, okay, will be equivalent to the weight. Okay, so that's why you remember that person saying that the weight of the object is 18 Newton. He doesn't mention that as 18 kilogram. Okay, because the weight is a force, but mass is not a force. So mass is just a magnitude. All right. Okay. So we have the weight of the object as W, right? And the acceleration will be equals to the gravitational force. So that's why we have, when an object is falling, so we mention that as A equals to G. Okay, so the weight of the object will be W equals to mg. Okay, for the hang object, so we have the tension there. So the weight, okay, so the weight right now will be 0. Okay, the weight will be 0 because the object is not moving. Okay, because the object is not moving. Okay, so this relationship is the same whether an object is falling or stationary. Okay, so when the object is falling, it will be stationary. All right, so let's have a look at the Newton's third law. Okay, so if object A exerts force F A on B on object B, for example, okay, and then the object B exerts force on FB on A, all right, and object A, right, then the forces have the same magnitude but the opposite direction. Okay, so let's have a look at to the example over here. So this is the Newton's third law.
Here I have a cart that has a fan on it, and when I turn on the fan, it causes the cart to move in this direction. Now here I have a sail, which I can put in front of the fan, just like this. Question is, which way will the cart move? Will it move this way again? Will it move the opposite direction, or will it not move at all?
What do you think? Is it A, B, or C? Will it move the same direction as without the sail? All right. Move opposite to the direction without the sail, or not move at all? So who chose A? So A is move in the same direction without the sail. Right? Nobody? Okay, how about B? So how move opposite the direction without the sail? You can raise your hand. So nobody answering B. Okay, Akil mentioned that it's B and not moving at all. All right. Okay, Elia mentioned that it's not moving at all. So let's have a look. So let's say it's moving on the opposite direction.
If I turn on the fan, you can see that the cart does not move.
Okay.
Now there was a force from the fan that, when the sail was not on the cart, caused the cart to move in one direction. When I placed the sail on the cart, you had one force trying to move the cart one way, and then you had another force pushing on the sail this way. These two forces were equal but opposite, and therefore the total force acting on the cart was 0, and it did not move.
Okay. So the important point over here is that you see the sail. So first, the fan will push towards that direction. Okay. And now, because there is a sail, the wind will going towards that side. Okay. So you have force acting on that side and also to that side. Okay. So that's why the cart is not moving. Okay. Congrats, Elia. Okay. All right. So I will stop here. Okay. So we will continue tomorrow. Okay. During the tutorial session. Okay. So lastly, please turn on your camera to take the attendance. Okay. All right. I'm going to count from 10. Okay. Get ready, everyone. Okay, from 10, all right, 9, 8, 7, 6, 5, 4, 3, 2, 1. Smile. Okay, give me one more shot. Okay, and another one. Okay, thank you, everyone. All right, so I see you again. Okay, so that's it for today. All right, any question you can ask me on the WhatsApp or email. All right, so bye-bye.
Thank you.
Thank you, Doctor.
You're welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.